Okay, we're good. Okay, uh, so let's get started. So, uh, uh, I think logistically, I think we have. So as I mentioned in the discussion, I read through the project proposals, and they're really fantastic, and I'm really looking forward to kind of the end result of these projects. What I would say is that don't think of this project just for this class, but think of it as like a kind of a project that you can present in your portfolio, like when you're in the job market or look applying for internships. Make sure that this project is something that you can talk about or put in your CV and highlight. Uh, so this is a very relevant topic for a lot of industrial positions, like any expertise or extensive projects in neural networks and deep learning is going to be really valuable. So try to use this as an opportunity to improve, to kind of augment your portfolio. Uh, and even like I'm typically open to, if someone wants to work on this beyond the semester, I'm usually open to kind of helping out or collaborating on this and making this more uh, like more of a more mature project. Or maybe if someone is interested in research, we can also think of publishing a paper if it comes to that, but that's like all beyond the course. uh, okay, so I wanted to as we are working through the topics in the course, I wanted to like give a kind of a big picture overview of like what we are doing. Like I know that we have been doing a lot of like mathematical background and kind of theoretical stuff. So I wanted to kind of tell you how all this is connected. So uh, okay. So in my mind, there are three pieces of the puzzle of kind of deep learning or kind of neural networks in general. Uh, One is called approximation. Can we approximate all types of like discrete and continuous functions with, I'm gonna write this as neural networks. Okay, so we are asking the question like how powerful are these in terms of representation? Like, can we represent all possible functions that we need to solve or learn? Can we represent all possible functions with a neural network? And based on like the Universal Approximation Theorem says yes, right? And especially we argued last time that if we use kind of the sigmoid or ReLU network, then we can approximate any continuous functions. Okay, so that's the first question. The second question is learning, right? Uh, Learning means like how do we train a neural network on given data, right? And this is typically our training data, right? And typically what learning means is that we have kind of a model parameter set, and we want to find the best values of the parameters or weights. Okay, so that's the problem of learning. That's the second big piece. And that's where actually we are right now. Like we've been last class, you remember we learned all these mathematical objects like gradients. We talked about convex functions. This all comes into learning, right? So the the modern approach to learning is using optimization. Okay. So what is the canonical process? Like we define a loss function, right? Represents the mismatch between, like, let's talk about supervised learning. This typically means a mismatch between the true label of a data point and the predicted label, right? And then we kind of sum up the loss for all data points and that gives us a loss function. And then once we have a loss function, right, we define kind of a learning algorithm. Typically, it's going to be some variation of gradient descent. And that's what we're going to talk about in detail today to find the optimal weights or parameters that minimizes this loss function. Okay. And then we need objects such as the gradient of a function, the Hessian, and we also see the Jacobian. We'll look at that today to define the learning algorithm. So that's where all this like math comes into play, at least right now that we're doing, is that we are trying to learn how to train a neural network. Uh, and then this learning algorithm like gradient descent is very general. It works for any type of neural network, or even if you don't use neural networks, like you can use some other type of learning, like support vector machines or kernel methods. There also this gradient descent can be useful. Okay. Uh, all right. And then so that's what we are gonna talk about today, optimization. So today we focus on optimization for neural networks and ML. We've already started that. We're gonna kind of continue that today. And then the third big question or puzzle is generalization. Does the trained model work well for new unseen data? Okay. And this is the harder problem and has a lot of unanswered unanswered questions. Even to this day, there are a lot of empirical ways of doing generalization, but we still don't have a good theory of generalization. Uh, Classical theories break down for deep learning, right? And we'll talk about that when we come to generalization, which will come after we finish the part on learning. Uh, the other thing about learning that I would mention, okay, someone has to be admitted, sorry. All right. Uh, The other thing I would mention is that uh, so far we've looked at neural networks with a single hidden layer, right? But as we will see that, and we'll also discuss this a bit today, is that there is a lot of benefit of having depth in a network where we have multiple layers stacked one after the other, and then you get like not just a network that is has a lot of height, where in a single layer you have a lot of neurons, but you also have these stacks of neurons one after the other. And that depth means that you have a kind of a big chain of a network. And then for that, you need kind of like back propagation. This is like a fancy, like not fancy, but kind of this is kind of almost the chain rule from calculus, but with some additional stuff. Like plus we need a DAG abstraction for networks. So we'll kind of start talking about that next class. But that's also part of learning or training. Okay. All right. So this is so my goal is to kind of we are gonna cover like all these three pieces of the puzzle in this course, and if you can get to the end of this, that would be a good point for us, checkpoint for us, and that's gonna be the majority of this class. Beyond that, there are kind of specialized networks like CNNs and RNNs. We might have one class on that, but we honestly we won't have a lot of time to go into specialized architectures for like vision or natural language. For that, you should think about another class that is specialized towards like vision or natural language processing. But like if we can kind of finish these three pieces of the puzzle, then we'll be in a good we'll have a good foundation of neural networks. Okay, so before we go into learning, I want to say a few things about uh, a few more things about approximation. So we've already like this part like we've kind of already covered so far. Like we've looked at the results and a proof sketch that like uh, if you have a whole bunch of ReLU neurons, then we can approximate any piecewise linear function. And as we add the more and more ReLU neurons, then we can arbitrarily approximate a function. And a similar construction also works for sigmoid neurons, where what we did is that with the sigmoid, as we increase the slope, it starts to in the limit approximate a threshold function, and we can put together two threshold functions to give us a pulse. And then when we aggregate all these pulses, we can approximate any function. So I wanted to show off something really fun here. Uh, it's called a kind of a graphing calculator. And what I want to show is like how can we actually uh, create some building blocks for a function to approximate them using neural networks, right? So in the class, we showed that uh, we can kind of we can use two sigmoids or threshold functions to represent a pulse. And then once you have a pulse, you can kind of shift the pulse anywhere you want, and you can also change the height of the pulse by doing weighted linear combinations, and that lets you represent an arbitrary function. I want to show uh, that we can do the same thing with ReLU. So a ReLU can also represent a pulse, but the construction is different. And instead of two sigmoid neurons, we need four ReLUs. So I wanted to kind of show how that works. So let's say we start with a constant when we'll discuss what the constant is. But this constant C is going to represent our slope. If you remember from the sigmoid construction, uh, right. So yeah, if anyone has questions, also ping me in the Discord. That way I can answer the questions because I'm not able to always look at the Zoom chat. So send questions in Discord and I'll keep an eye on that. Right. So the C here represents kind of the slope, and we'll see how. And let's define the ReLU function. So I'm going to represent ReLU with an R. So this is defined. Can anyone tell me how to define a ReLU function as a mathematical function? Anyone?
Um, it would be 0
Mm-hmm.
if x is
Right.
less than 0, I believe.
Right.
Less than or equal to 0, and then
Mm-hmm.
else it's just x.
Exactly. And one way to compactly say that is basically it's a max of 0 and x. And you can see once I did that, it actually shows me a ReLU function, right? So why does this work? Is if x is negative, right, then that represents this line, this part here. So typically Rx is always x. In general, it's x for all for positive values, but if it's negative, then we kind of cut it off at 0. So instead of having this, we have this if we just had like Rx equal to x, right? That would be like just the 45-degree sloped function, right? This is like y equal to x, but we when it becomes negative, we want to kind of cap it off at 0. So that's why, and then this 0 line is greater than this negative line. So if I do a max of 0 with x, then basically I get the ReLU function. Okay. All right. And now let's see what we can do with this. So let's say I want to kind of stack together two ReLUs, but I and then once I have this function, we see that we have this like this what is called like a kind of a sharp bump at 0 here, right? Now I can easily move this bump to a different location. So if I plot x minus 1, right? And you see that we've pushed this bump to 1, right? And if I keep both of them, you see that these two are. So now if I look here, right, you can see that this blue function is Rx and this green function is Rx minus 1, which is shifted to the right. And now when they're both, when x is less than 0, right, and everything is 0 here, between 0 and 1, so this is the point 1. Between 0 and 1, the blue function is like the linear slope, but the green function is 0. And then from 1 to onwards, they are both the same like linear slope, right? So what would happen if I subtract these functions? You can see that I now, at this point, from 1 to 2 onwards, the subtraction is, you can see that this function always differs by 1. So that's why we have this constant level 1 here, right? So let me get rid of this. So now we have this type of function here. And now what I want to do, I am trying to build a pulse. So what I want to do next is I want to kind of build up, instead of this at this point going to the right, I want to actually make it go downwards, right? So if I want to make it go downwards, then uh, what I can probably try is that at this point here, try a different type of, try another ReLU here. So maybe I can try R of x minus 2, right? So if I do R of x minus 2 here, okay, does someone else need to get in, or is it the same message? Or yeah, it's the same message, 10 minutes ago. Okay. So if I add x minus 2, you can see that this becomes another discontinuity, and this is pointing upward, but I want it to point downward. So all I can actually do here is just do a minus here. And now you see that at this point, it's actually moving down here. And then now at this 3, I actually don't want anything. So I want to negate this. So I can just add another pulse at x minus 3. And then you can see that now this kind of goes back to 0, right? Because a pulse is, it's positive between an interval, right? And then after the interval, it again goes to 0. So this is starting to look like a pulse, but it's not really a pulse. So what I actually want to do is kind of, this is kind of represents the slope of the ReLU. So I actually want to increase the slope. So I'm going to do a C here, right? If I add C's everywhere, okay? And if I zoom this down, right? So let me also reduce my value of C here. Okay, so let's make it 5. Okay, so now you see that the C, uh, as I increase C, the slope is increasing, and then also this pulse is also kind of getting narrower and narrower, right? So if I actually, I think I did it wrong. What I want to do is actually I want to put a C here. Okay. And then what I'm going to do here is make this -1, and make this -1. Okay. So you can see that there are ways to kind of combine these ReLUs to kind of create uh, this object that kind of represents a pulse, right? And now as I increase this pulse, you can see that actually I'm converging towards a pulse between 0 and 1. So I can actually maybe increase it like to 50, right? Or 500, and then you can see it's a perfect pulse, right? Between 0 and 1. So now you can see this pulse is comprised of 4 ReLUs. So to do this, I would need 4 neurons. I can stack the 4 neurons together in a particular way in a neural network, and then that would represent a pulse, right? So any questions on this so far? So this shows like with even with ReLUs, we can represent a pulse. And now let's say I have a general function x, right? And then I can say I'm gonna do a pulse like this that is height 3, right? And then let's say I do another pulse of -1. Mm. So you can see that I'm starting to create kind of piecewise linear functions, right? So let's call this like 4, and then say it's e of x minus 2, right? Plus 9 e of like x minus 3, and so on and so forth, right? So by doing weighted combination of these pulse functions, I can actually create arbitrary functions like this. Okay. So I wanted to just give a demonstration of generating these pulses with the ReLU network, with ReLU neurons. And once you have this pulse, you can actually approximate any function. Okay. All right. Uh, so the other thing I want to mention about approximation is like there are many different ways of kind of combining like these kinds of basis functions to create arbitrary function approximations. And like one thing that you probably seen in math is like Fourier analysis, so Fourier series, right? Where you can represent a function, approximate a function with kind of like a sum of sine and cosines. And typically, you might think of uh, sines and cosines as kind of like exponential functions, right? And then there is typically like a basis function here, right? So if you have a certain number of these, uh, sorry, that's not what I wanted to do here. What you need is kind of a constant here. So you're kind of combining these exponential functions with kind of a weighted combination of these exponential functions, and that typically can represent any function, continuous function, right? Uh, so that means that if you can, these you can think of as some sort of basis functions. Like this is like the nth basis function. And then you just do a linear combination of these basis functions, and you get a representation of your full network. So this might look like something like this, where you have your input. So this is your input, and then you have kind of all these inputs map into all these basis functions. And this typically is like a your basis function, for example, could be like an exponential, and then for every input you actually compute the basis function values based on some experience of like what basis function is useful for a particular problem, right? So in many cases, like a Gaussian is a good approximation of the basis function, and that typically leads to the radial basis function networks, which I'm not going to cover in detail, but I'll send you a link to last year's lectures that covers it in detail. So I would recommend you take a look at that, but we won't cover that in this class because we have more topics to cover. And then finally, your function representation is kind of a linear combination of these basis functions. Right? So this is like you have the weight of C1, weight of C2, and the weight of Cn. Right? And then this is your final prediction, which approximates the function x. Okay, so in some sense, like this, for example, is the structure of a radial basis function network. Okay, all right. Any questions so far? All right. So let's get back to the question of training. Like we are gonna now talk about how to train a neural network. And as we discussed in the section, training or learning the parameters of neural network is done using optimization. So we need to cover some ground in optimization. We've started to kind of talk about some of these objects, but now we are gonna uh, like s- move towards developing a kind of a full-fledged training algorithm that works for any neural network. That's kind of the goal in the next few lectures. Okay, so uh, from last class, we've looked at the gradient object, right? And we also looked at the Hessian. Okay, so if I have a function that goes from a d-dimensional real vector space into a real number, then we saw that the gradient object, right, it is also going from RD. It also belongs to basically uh, RD, right? And it was defined as you just take the partial derivative of f with respect to all the input parameters, right? So this turns out to be del f by del x1 up to del f by del x d. Okay, okay, everyone like comfortable with the gradient? Like this is gonna be the bread and butter of everything when we do backpropagation next class. So you should be very familiar with the gradient object. This is kind of the most important object in optimization, and we'll discuss why that is. Now, can someone define a Hessian for me? Like how do I write the Hessian?
Isn't it a D by D matrix?
Right? It is a d
Or
by d matrix. So I can compactly write it as basically every entry is basically a second derivative. So I can write it like this. I take the derivative at the ith and jth point. It's basically the derivative of s with respect to xi and xj, right? Where ij ranges from d, 1 to d. right? So I can represent this compactly in this way. Okay. And then we saw that a property of a Hessian is that it is symmetric, right? That's a very important property. And why is it symmetric? Anyone tell me why is it symmetric?
Because del ij is equal to del ji.
Exactly. So if I switch I and j, then the partial derivative remains the same. So that means only the diagonal entries are derivatives with respect to the same input, and the cross diagonal terms are all the same. That's why it's symmetric. Very good. We'll quickly see like how these objects come up in optimization. Okay. So I what I want to do now is we also need another construction where we want to understand if I have a function from, let's say, dimension d1 into into dimension d2, right? And the reason for this object is when we think of a neural network, right? We can think of, like, let's say this is like a particular layer, like layer like L1 in the network. The second layer is another set of neurons. Let's say it's L2. And they, let's say they're all connected to each other. Right? So we can kind of think of like if we have like D1 neurons in this layer and D2 neurons in this layer, then in a general network, after we do a linear combination, then apply a ReLU or a sigmoid, we get like these real numbers, right? So in this layer, you kind of have like D1 real numbers, and in this layer, you have D2 real numbers. So you're kind of transforming. So this is like a function f that transforms D1 real numbers, and as an output of this intermediate step, we get D2 real numbers. So we're transforming from D1 real numbers to D2 real numbers. So this is kind of a very common function in a neural network layer by layer. And we want to understand like what does the derivative of this transformation look like? So we need to kind of define a kind of this object. Like let's say the input here is X, right? Which is in D1. And then I can define a function f of X. Let's say I get as an output, which is Y. And let's say that belongs to RD2. Then what is this object that I take df by dx? I want to define this object. Like, how do we define this object? So this will be very important for us, especially when we're going to backpropagation. So we kind of need to construct this object carefully. So let's try to carefully define this. This function f, uh, so f of some input x, which is a vector, gives us like D2 numbers. So I can write them as Y1, Y2, and then let's say YD2. Okay. That's what I get. So I can think of this as like, I can kind of decompose this into like D2 different functions. So I can say that this is kind of F1 of X1. This gives me Y1. Okay. And now this F1 is taking RD and gives me just a single real number. Right? And then basically F is basically the same as these functions, F1 of X, like F2 of X, and FD2 of X. Okay. So we are basically decomposing this df by dx into d2 different functions which take the input x in d-dimensional space into a single scalar. So then for these objects, like we already know what the gradient is. We're going to define the gradient. So we can just stack together these gradients together to give me the object that I'm looking for, right? So that's what we're going to do. Now, here we're going to actually introduce a convention. And this convention will make our life really easy when we need to actually define the chain rule for multivariable calculus. And eventually that would lead to the backpropagation algorithm. But this convention is going to be very useful. And we'll see that with this convention, the traditional chain rule, if we elevate from scalars to vectors, it actually matches perfectly. So that's why we're going to do this convention. So we're going to say that if I have like a vector x, okay, let's say its dimension is d. Okay, this we are going to represent as a column vector. Okay, and when I have this gradient function, right? The gradient is for a function f from Rd into R. So we already know that this gradient object is just, we're taking the partial derivative of f with respect to each xi, and then we stack them together as a column. But instead, I'm going to keep them as a row vector. So this is going to be like, that's the convention. And it's a reasonable convention. It doesn't really harm us. Like there is no mathematical issue there. They're all like set of D numbers, but I decide to represent the gradient as a row vector because the gradient is basically taking these partial derivatives and stacking them together. I'm just going to stack them as a row vector. And just with this convention, like we can easily define uh, the object called a Jacobian, which is for a gradient from a vector to another vector. And then with that, the chain rule actually plays very nicely, which is why we have this convention. So this is going to be basically, I'm just going to make sure that this becomes a row vector. That just means I'm going to, instead of stacking them vertically, I'm going to stack them horizontally. That's the only thing. Okay. So this is always going to be a row vector. Okay. All right. So now if we apply this convention, then if you go back to our previous function, we had this function. Let's call it, again, let's just call it f. And now from RD1 to RD2, if I need to define the gradient now for some input x bar, well, instead of calling it a gradient, I'm gonna call it something else, but it's kind of a derivative. But I'm gonna just write it as, like, let's say it's x is in D1 dimensional space and goes into like y, right? Then this derivative, which is dy bar by dx bar. Basically, we know there's this y is basically y1 up to y d2. Okay. And then for y1 is basically like a function f1 of x. And then last one is a function fd2 of x, right? And then the first derivative is going to be the first row, which is going to be f1 with respect to all the inputs, d of x1 up to f1 with respect to d of xd. And then here we're going to stack up all these rows. And finally, the last one is we're going to d of f d2 d of x1. And this goes to d of f d2 divided by this is x d1 d of x d1. And now we have this full matrix which represents the derivative of y with respect to x. Okay. And then this object is called the Jacobian. Okay. What is the dimension of this matrix? How many rows and how many columns?
D2 rows
Right.
and D1 columns.
Exactly. So D2 by D1. Very good. So now you can think of this Jacobian or derivative object is like you have an input x, like in space R d1, and then you apply this Jacobian, which is d2 by d1. So the Jacobian is like this object dy by dx, where x and y are now vectors, right? And then this is d2 by d1. And if you kind of multiply the matrix by this vector x1, right? Then what you eventually get back is kind of your full this actually becomes your uh, derivative with respect to y. So you can think of like a small incremental x, and this would give you kind of a small increment in y. Okay. So you can see that all the dimensions match up properly. So why is this useful? So let's recall the chain rule. Right? What is the chain rule? So let's say I have a function y. Let's first do the chain rule for scalars. So let's say y is equal to like function of x, and then z is another function of y. I want to find out what is dz with respect to dx. Okay. And now the chain rule tells me what? Can anyone tell me the chain rule for scalars?
I I don't know specifically for scalars, but I know it's the derivative of the outside function times
Mhm.
the derivative of the inside function.
Exactly. So you can just break it down as z depends on input y. So from here we can compute dz by dy, and then y depends on x, so we get dy by dx. And like when I was a kid, we just learned this like this dy cancel each other, and we just get dz by dx. That's how we would remember this. But that's the chain rule. Uh, Now the nice thing is that when we extend now, if let's say all uh, these are all, let's say now vectors. So let's say y1 is equal to now function of x vector, okay, and then z is another vector which is g of y vector, okay. Now what are the dimensions? Let's say x1 x bar is in dimension RD1, y bar is in dimension RD2, and z z bar is in dimension, let's say D3. Okay. So now f is a function that takes RD1 into RD2. Okay, I can write it much like this, where I just write F here, which means F is the map from D1 dimensional space to D2 dimensional space. And then G takes this from RD3. So I can write it like a function, a vector X belonging to RD1. It gets mapped to Y bar, which is function of X bar. And that gets mapped to Z bar, which is now G of Y bar, which we can write further as G of F of X bar. Now, because of our convention, we can exactly rewrite the chain rule for this. Now, when we do the when you do the chain rule for vectors, now these derivative objects that we have, they are going to be matrices now. Okay, so now if I want to do the chain rule in this case, we actually have the exact same thing. We can still do d z bar by d x bar. Okay, and then this is going to be d z bar divided by d y bar, and then d y bar divided by d x bar. Okay, and this makes sense because z is this function g of y bar, so z depends on y and y depends on x. But now instead of the scalar case, these objects are actually now matrices. So this is a matrix, this is a matrix, and this is a matrix. So we need these matrix dimensions to add up. So now let's see, can we figure out what dimensions do we need here? So if you look back here, when we are doing from D1 dimension to D2 dimension, y bar x from x bar, it's the row is the number of D2, which is the dimension of the output. And then the column is the dimension of the inputs, right? So if we apply this here, what should be the dimension for this part here?
Would it be D2 by D1?
Exactly. It will be D2 by D1. What about this one?
D3 by D2?
D3 by D2. Now, right away, you can see that as matrix multiplication, sorry, D3 by D2, right? Right. So you see that this D2 and this D2 matches. So matrix multiplication wise, we are consistent. And that's the beauty of the convention that we did. That convention made sure that this actually works out. And now that means if I multiply these two matrices, right, then this matches this. So this should result in a matrix of dimension D3 by D1. And if you check the output here, then Z is what? Z is in D3, which is the output. So this also is going to be D3 by D1. Okay. So with that convention, the chain rule properly generalizes to vectors, and we don't have to worry about a different formula. We have the exact same formula that we have for scalars, but for vectors also. Okay. So this is like the vector chain rule. All right. Okay. So let's take a break now. It's 9:06, and let's maybe come back at 9:15. Okay, and then we'll resume the class. All right. Okay, is it okay to restart? All right, looks good. Let's resume. Okay, so we have all the machinery we need for kind of doing gradients, Hessians. Uh, Also, just to check, everyone can still see my screen, right?
Yeah, we can see that.
Okay, great. Thank you. So we have we've kind of defined all these objects here. Uh, so now we want to kind of think about we have so as we talked about this at the beginning about uh, like this recipe for learning, right? Where we define a loss function. We saw different loss functions for different objectives, right? For linear regression, for logistic regression, we saw loss functions. And then we saw that in general, we can always take a derivative of the loss function and we set it to zero. And that's how we solve for the parameters. That's the kind of the general way of doing that, right? So that's actually going to be the recipe for us also. But we'll see that in general, like we cannot always uh, the loss function. So if we have a loss function, right? And the loss function typically is going to be some function of a bunch of weights, right? We define this depending on our problem, right? So for example, for linear regression, this could be a linear function, and then we take example, like example is this could be if you're doing a linear function, then this could be kind of a linear combination minus the actual label, right? And then we can do a square, right? And then if this is the loss function, we saw that we can take the derivative of this, right? And then we set it to zero, and then we can calculate the optimal weights. Now, this is a very lucky situation where for this case, this loss function is really, really simple, right? So this may not always be the case, especially for neural networks. We're going to have very complex loss functions. So we need to actually find numerical ways of finding the best set of weights to minimize this loss function. So for example, we're going to see how we can use the gradient and Hessian objects to approximate this minimization problem. Okay. So if we think of a picture, this is the canonical picture that we have in mind. So we have loss of a set of weight parameters. And let's say the weight is represented by the x-axis. In this case, I'm representing like as a single parameter loss function. In general, W can be high dimensional, but I'm just representing it as a simple function. And let's say we have this type of loss function objective, right? What we want to find is we actually want to find this point because this is the point where my loss is the lowest, right? So in the case of linear regression, we can actually optimally find this point because we can solve this exactly. But that's not always the general case. So that's why we need methods to actually iteratively find this loss function, right? So we want iterative methods. Okay. Now, in general, this loss function is going to take some vector of weights in, let's say, d-dimensional space, and this is going to be like a function from a d-dimensional space into a scalar, right? So this matches the types of gradient Hessian objects that we've been studying so far, right? Now, if the loss function is a complex object, we cannot directly analytically solve it. So what we want to do is that we want to use these gradient and Hessian objects to kind of tell us where to move in this space, right? So we might actually be starting at some point here, right? And then if this is my initial W, right? You can see that we can, if you could move in this direction, then we can move towards the minimum, right? We need a signal that tells us that this is the right way to move. Okay? So how do we get this signal? One signal could be like if I compute the gradient, so you can think of gradient as like the slope at this point. And the slope, you can see that the slope at this point is increasing in this direction, right? And if I look at the opposite of this increasing direction, that means that opposite direction is this way. So if I want to move in this direction, that means I'm actually moving in from W0 to W star, right? So in some sense, this gradient moving in the opposite of the gradient direction tells me the way to move towards the optimal here. So this is kind of like a high level sketch of how we can use the gradient information to tell us which way to move. Okay? Is this making sense? Yeah? All right. Okay. So the gradient and the Hessian, these objects tell us actually how we can actually find the optimal, right? Now, if we were to find the optimal of this point, that would represent kind of a, a slope like this, right? So what does this slope represent here? How can we characterize this slope here? What is the gradient at W star, or the derivative of L at W star?
0.
0, exactly. So we want to find a W star such that W star, if we take the derivative of L with respect to W star, that becomes 0. That's what we are trying to find. If we find this, then we would actually find a possible optimal point. Okay? Now, the problem is that if my loss function looks like this, I could have a loss function that looks like this, right? Then if this is loss and this is my weight, then here the derivative is 0. Here also it is 0. Here it is 0. All these points are 0. But you can see that the minimum point is exactly like this one point. So just with the first derivative, we can never tell whether it's a minima or a maxima, right? So this is like a local maxima, and this is a local minima. To characterize the local minima, we need an additional condition, right? So if I look again at a picture of a shape like this, for this to be a minimum point, right, we can characterize it using second order objects, right? And what is the second order object that we learned in this class for these gradients or taking these like differential objects? Anyone?
The Hessian.
The Hessian, exactly. So if we can compute the Hessian, then we can actually define the curvature, like how is the gradient changing, and that curvature tells us like whether it's a minima or a maxima. And for the loss, we want to minimize the loss so that we have a better learning algorithm. So we want to find a point where the gradient is 0, and also the Hessian is actually what we call positive semi-definite because it's a matrix. If this were a scalar function, then we would just say that, for example, this case, we take if this is L and W and these were scalars, we would just say that, okay, at the minima, we want this to be 0, and we want the second derivative. This will be the second derivative. For a scalar, this will just be a single number. It has to be positive. Okay, that's for a scalar case. Because why is that the case? Because here you can see before the minima, you can see that the slope is going downwards, or it's a negative gradient. Whereas when we go beyond the minima, the slope is positive. So this is a positive slope and this is a negative slope. That means the rate of change of the gradient of the second derivative is positive for a local minima, right? Now, if we are in a space where our input is d-dimensional, now we need to deal with the gradient object. So in this case, the condition is going to be that the gradient of L at W star, which is the optimal point, this has to be 0. Okay, this is the local minima condition. And then we need the Hessian object at W star. This needs to be, because it's a matrix, we can no longer say it has to be positive, but it has to be positive semi-definite. So that's what we represent here. This is called a PSD matrix. So that's the condition for finding a local minima. Okay. Now, when we say PSD, what that means is that for any vector x, in RD, x transpose this H, this Hessian times x is always positive. That's the definition of PSD. Okay, and we covered this in class before. So to characterize a local minima, we need the gradient to be 0, and we also need the Hessian to be positive semi-definite, or PSD. Okay, so that's the condition. So let's see how we can use these notions here. So let's talk about another calculus theorem, or kind of an important notion, which is the Taylor series expansion. So in calculus, we can expand any function in the Taylor series. Okay, and in a 1D case, this is what it looks like. If I want to find x at a nearby point, x plus del x, okay, then I can expand this using a power of derivatives, right? So this is going to be, we first say it's f of x, and then the second term is going to be delta of x times the first derivative of x, right? So f prime of x. Okay, so this is like the first order approximation for the function, right? If I stop here, then I have the first order approximation, but that's going to be less accurate unless I add more terms. So I can add more terms here. The next term I can add is like 1/2 of del x square times what do I have to put in here for the second order approximation? Anyone? So here f of x is the zeroth order approximation, right? It's the function, it's assuming that the function is the same at x and x plus del x, which is not true. So we need to, so then we add like the first order approximation, which is del x times f prime of x. And then what is the second order approximation term that I can add here? What will it be? It's going to be something about f.
F double prime.
F double prime x, exactly, the second derivative of x. Okay. And there are going to be other higher terms, which are higher terms in terms of the cubic terms of x, right? Which we are not going to think about. These are like more terms which can make it more accurate, right? And now we can think of this is kind of the first order approximation. And then this part is the kind of the second order approximation. And that's where we're going to stay in terms of optimization. We don't do higher order than this. In general, for most neural network training, we typically just use the first order approximation, and that leads to the gradient descent algorithm. And then when we do the second order approximation, that leads to Newton's method, which is more accurate, and we'll see all of those. But first things first is if we try to extend this into a vector version of Taylor series, then what do we have? So now instead of x being a scalar, let's say x is now in Rd. Okay. And then if that is the case, then how can I write this object? So f, let's say f is now a function from Rd to R, and I want to compute the approximation of f at x plus delta x, where delta x is also a vector, a small vector direction, right? We are kind of this is also kind of the idea of directional derivatives, right? We if I try to find the directional derivative, we kind of take x and move it into a certain direction. So del x is also in the same vector space. So now I want to see if I move in that direction, then how do I approximate this function there? So it's going to be, the first term is going to be the same. It's going to be f of x, okay? And now the second term is going to be similar to what we have here, del x times f prime of x. Now, f prime of x, what type of object is that? Is that a vector or a scalar? For this case,
Vector.
it's a vector of the same dimension d, right? So, and then delta x is also a vector, but the function maps vectors to scalars. So here, corresponding to this, I still need a scalar. So how can I get a scalar from these two objects here? The gradient and the increment delta x. If I just do delta x times the gradient of f, so instead of f prime of x, I'm going to replace that with the gradient, which is a d-dimensional vector, and delta x is also a d-dimensional vector. From these two, I somehow need a scalar. So what operation can I do to get a scalar from these two vectors?
Transpose.
Right. So I can transpose this and take the dot product here, right? That would give me a scalar. Yep, exactly. Very good. Now the second case is again here. What would I replace f double prime of x with? This is the second order derivative, the second derivative. So we know that for a vector case, what is the corresponding object here? Right, it's peaking somewhere up here.
The Hessian.
The Hessian, right? So we have the Hessian, okay? And then With the Hessian, we need to multiply del x square. But del x is a vector. The square doesn't make sense, right? So the only way to make this a scalar is that we take the quadratic form here, right? So this is like a del x transpose times h times del x. If I do this, right, then we know that this matrix times a vector gives us a vector, and this is a vector transpose times a vector, so we would get a scalar here, right? So now this is now the matrix or vector form of the Taylor series, okay? So this is a very important expression to remember because this is from where we're going to derive all of our optimization algorithms, okay? All right, so far so good. So now let's start doing approximations, right? So let's first do like a first order approximation. Our goal is to find a kind of a rule for deriving or kind of a rule for finding a direction in which we want to get to the minimum of the loss function or function f in this case, right? So let's say x is a kind of a local minima, right? So kind of, and x is a vector here. So kind of like x is this point here. Now, if x is a local minima and I move slightly like in either direction, I might go at this point, which is like maybe x plus delta x, right? And if this is a local minima, what does this tell us about the value of the function at point x plus delta x? Will it be greater than f of x or less than f of x? If x is a local minima. If I perturb x slightly and move to x plus delta x, which of these quantities will be bigger or smaller?
X plus delta x will be larger.
Will be larger, exactly, because f of x is supposed to be minima, so it should be less than f of x plus delta x, right? So that's what we expect. Okay, and now let's say fx plus delta x, we are going to approximate using the first order approximation, so we're just going to keep this part here. Okay, so let's approximate this part with f of x plus del of x transpose gradient. Okay, now from this, what do we get? From here, this f of x and this f of x cancels, so we have that 0, or we just write it like, if we just do this, we get del x transpose with the gradient is going to be greater or equal to 0. Okay, so now we can think of choosing a direction, right? We want to choose a direction where so let's say we choose Oh, sorry, I made a mistake here. This is not a gradient, right? This is going to be delta of x. Okay. So if we choose delta of x to be equal to the negative, right? So what I'm trying to do here is I want to decide what is delta x, right? If I choose delta x to be the negative of the gradient of the function f, right? What I get from here, this equation above is this becomes minus delta f transpose delta f, right? And this becomes equal to negative of the norm square of delta f square, right? And we say that this term is greater than or equal to 0. That means from here we can say that this implies that the norm of delta f square is less than or equal to 0. Okay. But we know that norm is always non-negative. So if I take the norm here, this has to be greater or equal to 0. And from these two, we can conclude that del f actually has to be 0. Okay. So the first order condition, if I want x to be a local minima, that means that the gradient at x needs to be 0. We kind of proved that here. Okay. So to find a local minima, we first need to make sure that the gradient is 0. Okay. And then if I do the second order approximation now, right? And this is going to be f of x. And this is going to be plus 0 because we show that at the minima del f is 0. But the second term now survives. So the second term is going to be 1/2 times delta x transpose h delta of x. Okay. And now we know that this is going to be smaller, right? This is smaller than f of x. So from here, the condition is that you're going to require that 1/2 del x transpose del x. This actually needs to be positive, right? Because if this is positive, right, then fx plus a positive number will be a bigger number, which tells us that the x would be a minima, right? And this means that H is the positive semi-definite matrix. Okay. All right. So we proved the first order and second order conditions for a local minima, and we're going to use that to find local minimas. Okay. So what was the first order condition? The first order condition was that del x needs to be negative of del of the gradient of the function at the current point x. Okay. So what is delta x? Delta x is a change of x, right? So let's say I'm doing an iteration where I'm trying to find the values of x0, x1, and I want to lead to a point x star that is going to be my optimum. Okay, the minima. Okay, so now I can use this rule to define a strategy for actually iterating through the values of x so that we can reach a minima. Okay, so what is that rule? So what is xt? Xt is like the difference of x, right? So delta x is like, let's say I'm currently at the tth iteration and I want to move to the t plus first iteration. So delta x I can write as the difference between xt plus 1 minus xt, and that is supposed to be, if I set this to the negative of del of the gradient of the function at the current point x of t, then that tells me that this rule will actually help me move towards the minima, right? So now let's rearrange this. That means that the next point, xt plus 1, should be xt minus the gradient of f of xt. And all I'm going to do is like add a eta here, which is called the learning rate. So this controls how fast we move towards the gradient. Okay. And this is the famous gradient descent rule. And this is probably the most widely used learning rule in neural networks, right? Gradient descent. And that's where it comes from. So even if you forget everything else, if you remember this, you are in good shape. You can just use this rule to, and with this rule, applying this rule to your neural network, will actually let you find very good parameters for your network. So in general, when we are talking about neural network, we're talking about this weights we are trying to optimize. So this, for the weights, the equation looks like this. The next iteration of the weights is going to be the previous iteration minus some learning rate times the gradient of your loss function at the current set of weights. Okay, so this is the most popular form of the gradient descent rule. Okay, so if we use the first order condition, we get this gradient descent rule. And now we also have second order information, which is the Hessian. So let's see what happens if we think about the Hessian. Okay, now if we so see, like if we actually want to apply gradient descent, we actually need to know this object, which is the gradient of the loss function. So we need to compute these gradient objects, which we've practiced a lot, right? So if you find loss function and we know how to compute the gradient, we can apply the gradient descent rule, right? Now, if we are also able to compute the Hessian object, that means that we can actually possibly do better in our optimization, or actually reach the minima much faster. Okay, so what's the idea for the Hessian method? And that's called that is what we call Newton's method. Okay, what is the idea of Newton's method? It's about using a method for finding roots. Okay, what's the idea? Why do we need to find roots? In order to optimize your loss function, we know from the first order condition that what we need is, if we have a loss function, we need to find a point in the loss function where the gradient is 0. Okay, so if you think of and then if this is a general function, then this will be like del of f equal to 0. Now, when we take the gradient of a function f, we actually get another function which is we can call g. Okay. Now, if you have a method for finding the roots of g, that is the values for which g equal to 0, then we can actually find where del f is equal to 0, right? And that's the idea of Newton's method. So how does it work? Let's say we have a general function of x. Let's call it like g of x. Okay, and this could be like a function that maybe looks like this, something like this. Okay. The idea of this is basically, let's say this is the current position x1. Okay, and uh, I'm trying to get towards closer to a root of this function, right? So what I'm going to do is I'm going to try to compute the gradient of this, and this is going to be like this point here. I'm going to see where does this slope actually intersect the x-axis, and that's going to be my new approximation of x, or x2. Okay, and then here it's hard to see, but I'm going to again find the value of the function. So this is g of x1, and here we have like g of x2, right? And then as I do these successive approximations, I gradually find points that are actually values where g of x is equal to 0, right? So the rule is basically, uh, I can say this is like delta of x, this difference between x2 and x1. So what is happening is that, uh, how do I find x2? x2 is equal to x1 minus delta of x. Okay, what is delta of x? Delta of x I find by this triangle. This has slope g of x1, right? So the slope is at del of g of x1. That's the slope. That's equal to the vertical height. The vertical height is the value g of x1 itself. And we divide that by like del of x. And from here we get that del of x is equal to uh, g of x1 divided by del of g of x1. Okay. All right. Okay, so what is the rule here? Then the rule here is x2 equal to x1 minus g of x1 divided by del of g of x1. Okay, now what is our goal here? Our goal is that g is del of f, and we are trying to find the minima by finding the point where the gradient is 0. So I'm going to substitute g equal to del of f. So if I do g equal to del of f, right, what do I get here? This is going to be x2 minus equal to x1 minus, we have del of f object here at x1 divided by del of g, and is going to be del of f, which is del square of f. Okay, so that's the rule. Now, so this is kind of a different rule for finding the next iteration of x, but this is in terms of both the first order object, which is the gradient, and the second order object, which is kind of the second derivative. Now, this is for I have shown this for a single scalar uh, function, but if this is a vector value function, then this is going to be the Hessian object, right? But the Hessian, I cannot divide by the Hessian. So instead of dividing by, what operation can I do with the Hessian if I want to like simulate a division? If x has to be like a vector value function, then how can I get the same as a division by a matrix? So this part is going to be just getting the gradient of f at the current iteration x1. But here, if this becomes the Hessian, how do I divide by the Hessian and get the same get the same impact as a scalar? With a scalar, I can divide by the gradient, which is a single number. But if I need to divide by a matrix, what is a valid operation? Like what matrix operations is similar to a inverse, is similar to a division? I think I told the answer. Anyone?
Inverse then?
Exactly, inverse, right. So if I just take the inverse of the Hessian, that gives me like division by the matrix. That's kind of the idea. So from here, this is actually Newton's method. So the Newton's rule is basically the next iteration of xt plus 1 is going to be xt minus inverse times the gradient of f at xt. Okay, this is Newton's method. And for our neural network or machine learning, this will be basically wt plus 1 equal to wt minus some learning rate maybe times inverse of the Hessian times the gradient of the loss function at the current weights Wt. Okay. Now, as we can see, this actually leads to faster convergence. I mean, I'm not going to prove that to you, but this this lets us reach the minima of the loss function much faster than the gradient descent method. Now, if this is faster, then why would we not use this, and why do we always use gradient descent? Like, what is the problem here with using this for doing optimization? Can anyone see a problem here computationally? Like, what is this object H inverse? H is a D by D matrix, right? Where D can be like millions of parameters. In a real network, D would be like millions of parameters at least. So D by D is like maybe 10 to the power 12 size object. And you have to take this, an inverse of this massive matrix, which is computationally very expensive, right? So kind of this inverse is expensive, which is why we never really, in practice, actually use Newton's method. Okay, so that's why the gradient descent is the most popular method. But we'll see that there are some methods we're going to get to, like Adam. And like RMS prop. So RMS prop was the first breakthrough that improves gradient descent by somehow approximating the effect of this inverse Hessian. And then Adam makes it much better. So these methods, so right now, the most popular method for neural network training is Adam. And the reason Adam is so popular is because it's somehow doing a cheap approximation of this Hessian inverse. And that's how it kind of gets it to work. Okay. So we'll stop here, and we'll kind of continue next time, and we'll kind of discuss some more techniques for optimization. But that's kind of the high level idea. So what we've covered is we've seen that from the rules of optimization, we can find this rule gradient descent. And this is the most popular rule. And this only involves computing the first order gradient object. And then if you do Newton's method, which is much faster, it gives you like what we call quadratic convergence. But the problem with this is that it involves this Hessian and taking inverse, which is very expensive. And that's why in practice, we never really use the second order methods. What we use is something between the first order and second order method, which is the Adam method or RMS prop. And this, what it does is kind of, it approximates the impact of inversing the Hessian object. So, and that's the state of the art. This is state of the art optimization. And we are going to talk about this more in a later lecture. Okay, so we are over time. So let's stop here. And next class, we will kind of wrap up optimization and start with backpropagation. Okay, all right, very good. Any questions so far? Very good. Right. So if there are no questions, we can end the class. And like with remote, it's hard to do like maybe after class office hours. So if you have any questions, you can always ping me on Discord or kind of like send me an email if anything about assignments or anything else you want to talk about. All right. So if nothing else, like let's stop the class for today, and hopefully I'll see you on Monday in class. Thank you.
Thank you.
Thank you.
All right. Take care.